the getting rid of the log n. Yeah, I'll talk about it. The quick answer is just that you realize that it's a DAG because I just need to go from left to right or from right to left, but not both. So you can solve it in n square. No, but so getting rid of the log is done because we can notice that when since a path will, if these are my obstacles, here are my obstacles, and the shortest path from here to here might have to go to the left and then go to the right. But if my verticals, if the segments are vertical, or if I'm on a train and I need to also only go to north or east but never go back, I cannot have cycles. That is, I can orient everything. So I'm only moving only to the right or only moving only to the left. So it's two different problems that I need to check both of them. But the check is done by just making a DAG. And once it's a DAG, then we know that Bellman-Ford and Dijkstra are actually merged together into one single algorithm, which just is one path, one linear path on all the vertices. So we are using the DAG algorithm. The DAG, DAG. So again, Kuhn is used to take an input graph and ask, is this a DAG at all? And if yes, then what's the topological order? And if it's not a DAG, then show me a cycle. Once I find the topological order, then I can find the longest path, for example, which is NP-hard in normal graph. If I'm looking for the longest path instead of the shortest, or I'm looking for the shortest, and but I want to do it with only one path on the graph, or many other applications. DAG makes life much easier. So I first run Kuhn to check if this graph is a DAG or not. In this geometric case, where all the segments are vertical, then the shortest path will never have to go back. And the shortest path from here to here will never have to go back left and right or up and down. So I can just connect, I can make it a DAG by just look at one segment, look at another segment. If part of the input is at this point, Pi sees this point Pj, and I'm only looking for path that goes from left to right, then I'll direct the edge between them so it's from left to right. And all the edges are directed from left to right. So left to right meaning that the x-axis will increase. It can go up or down, but never to. But the starting point is to the left of the ending point. Sure, it's So I'm given an undirected graph and ask how many edges do I have in it. Yeah, I can mention it. One second. Okay, let's start. Can move it a bit to here, and recording. Fine. We're going to speak mostly about dynamic programming problems and applications today. A few of the questions from the midterm. The midterm was all questions, I think, from homework 3 and 4, or some combination of these questions. So none of them was really easy, but it was questions that you had earlier. I think most of them was not, yeah, it was either questions from the preparation part or questions that you were asked to submit on Wednesday. One of the questions in the homework asked for the following question. We are given a graph, we are giving two sets of vertices, one called A, let's say A1, A1, A2, A3, one called B, defined by B1, B2, B3, and I'm asking for the shortest path from any vertex of A to any vertex of B. That is, find the minimum for every A in the set A, and the minimum for every B in the set B of delta A, B. Which was a here is to just say here is Tucson, here is Phoenix, and I'm looking, and when I'm asking what is the distance from Tucson to Phoenix, I'll ask what is the distance between the nearest point of Tucson to the nearest point of Phoenix. The two smallest houses out there. Not what's the maximum distance, but what are the two houses that are the closest to each other. And this question I actually mentioned that you can solve in a few ways. You can solve by either changing the code of Dijkstra, or you can solve by changing the graph. So let's see first how to change a graph, because this is a more general technique that can help us in quite a lot of other questions, but it's less obvious. So the solution goes as add one new vertex that I'll call S0, and I'll ask, hey, from S0, connect it by an edge to every vertex of A, and the weight of each one of these edges is 0. So again, S0 is a vertex that was not in the graph originally. I just added this vertex, and I'm connect S0 to every vertex of A, only to the vertices of A, and the cost of this edge is 0. So it doesn't cost me anything to go from S0 to any of the vertices of A itself. Similarly, from B1 and B2 and B3, I'll add edges whose cost is 0 as well, and add yet one more vertex, not original in the graph, called it, say, T0,